So I've been doing a little work on the Monarch, and I've got a few things accomplished. I rewired all of the cloth insulated wire that was in the control panel on the left side behind the module. I have temporarily routed it. It's not as neatly tied as OEM because I don't know what else I might have to troubleshoot once the lathe's been running for a while, so I didn't want to have to untie it just to get back into it. And so we went with what I had on hand. I had some 14 gauge. This is UL 1015 TEW, MTW, one of those multi-rated wires. It's nice and flexible. I don't have any issues with routing or anything. And so I had an assortment of 14 gauge, 12 gauge, and 10 gauge. And so we'll kind of take a look at that and a little bit on the crimping. So bring in the camera, we'll get a little close up, see what's going on. So this is the wiring I was using. Here's what came out of it. We have the insulated connectors. I don't really like these. They're actually crimped pretty well, but these have a bad habit of non-ideal situations where they're being used in, and improper crimping. These appear to be used with the right tool. They didn't fail or anything, but I just do not prefer this style. One type we have here, this is what's called a barrel crimp. It's the kind where it crimps and it strain relieves by pinching the insulation, and then it's got the wire crimp further out. This is what's used typically in automotive situations, a lot of professional electronics and equipment, coming off factory floors. I did a test crimp with what I had. I don't have the proper crimper to do this. This one turned out alright. So what I just did was just a regular crimp, using a crimp tool that I trust and I like. It produces good quality crimps. And it's not a high dollar tool by any means, but it's a very stoutly built one. And it crimps really well, and that might be a little bit too much space there between the insulation and the start of the terminal. This is just when I pulled out of the junk pile. And so once I'm done with that, I'll take a medium wall thickness adhesive lined heat shrink and just run that up. And so that'll provide the strain relief on the wire. It's actually pretty stiff right there. And so this is what I did all my repairs with, that style of crimper. And here's just a piece of the wire. You can see how many conductors are in here. So that's much better than a THHN. So if you have a chance to use this, like I said, this one's spec'd as, well, it's got a lot of specifications, but it's a MTW, THHW, or it's also a 1011, 1015, 1230, 1335. So essentially it's a UL15, 600 volts, 105 degrees Celsius, moisture resistant wire. So these are available in any color, well, not any, well, I guess if you paid enough money, any color, but multiple colors. I just went with all black because all my wires are labeled with the number of the wire wrapped around the end. So yeah, I mean, this comes in gauge ranges, I think pretty commonly from 18 down to about 6. It's a pretty good wire, I like it. So I got an outlet over there, 50 amp breaker. Don't need a 50 amp breaker to run a 10EE. However, I do have welders and stuff that could benefit from having that much current available. So basically we just got a regular household panel. I had 2 spots left, so I was able to bring in a circuit for a 240 volt breaker, 50 amps, and it's a 1450R receptacle. So kind of looks like, well, Kind of looks like the shadow of the camera's in the shot. So it's one of those guys. Basically 2 hots, neutral and ground, and a 50 amp rated plug. Pretty typical for modern stoves, and also handy if you have an RV that you like to park in your driveway, so your cousin Eddie can empty the shitter in the storm drain. He'll be able to plug into that. I just got a piece of plywood in there. Those black lines are just Sharpie where it kind of scribed out where to cut the hole. And I just didn't have any drywall handy, and it's the garage, so I just cut a piece of 1/2 inch plywood and stuck it on there. We'll paint it white. So here's my power cord for the lathe. Got a 1450P on there, and connect to some SOOW. It's a 6 gauge 4 conductor. I'm bringing the neutral to the lathe. Not using it yet, but I might in the future for some 120 volt, powering DRO or some other accessories. So we'll go around the back of the lathe and just see where I brought the power in. It's pretty typical. Alright, so here we are at the back of the machine looking at the new junction box. So nothing special here. Got the 6 gauge SOW coming in, and it's a little bit overkill, but I'm running 25 feet of extension cord, so it's probably just somewhat justified. So the neutral isn't connected to anything. At some point I might install a neutral bus just to make it easier to run 120 volt devices off the lathe. For now it's not connected to anything. And this guy, that's the 3rd phase that the only purpose it serves is to power the coolant pump. And so here we have 2 hots coming in for the 240 volts. So the way we have these connected are just some Thomas and Betts split nuts. And so you can see, you just put your terminals in there and tighten the nut down. Got it wrapped. Some of this thick, you can see how thick it is. Just meant for providing some abrasion resistance and a little bit of protection to the terminals, and then topped with a little electrical tape. And then just your standard Crimp terminal screwed into the back of the enclosure for equipment ground. So that's pretty much it for the power for now. We'll take a look at the other electrical systems on the lathe and see what we've done. Alright, so everything is 100% working. I'll go over a few things I've fixed. So this is the module. It wasn't in the first video. I had it out. This has been thoroughly checked, and every component is functional. So it contains, you can unscrew this, it pulls out, and then there's a couple of screws that holds the case together like a clamshell. And inside is just a bunch of diodes, some capacitors, resistors, just various networks for controlling the analog feedback for the drive system for speed regulation and load compensation. So you flip this down. So anyway, these are the thyrotrons, and they act as rectifiers to provide DC power. And so the controls, the module is what's determining, based on your input for spindle speed, how long to fire these. And there's not a really good video on how thyrotrons work the last time I looked. So I may do some simple little video that kind of explains it. But essentially all your components here, these are providing power to the armature, the DC motor. This is providing power to the field. These 2 transformers are just heater, supplying current to the heaters for the 2 thyrotrons. This big guy over here is 2 braking resistors. So when you change spindle speed, and the change in speed and the corresponding change in current is great enough, the analog circuitry detects that and knows that you want to change the speed. So if you're wanting to slow down, then it will essentially remove power from the motor, short circuit across the motor terminals, and electrically break it. So these right here are real high wattage resistors. And the first time I used the machine pretty heavily, of course all the oil that was on those wires baked off and started smoking. So it was a little bit alarming, but I figured out pretty quick what was going on. So it can get hot, and so that's why they're wound around these ceramic fixtures here. So that's just probably some nichrome wire, measured out to be 8 ohms. I'm not sure the wattage off the top of my head, maybe 500 watts a piece. Not 100% sure on that. But they only operate for a second or so. So it's not like when you slow down the motor, it breaks really fast, like within a couple of seconds from max speed. The specs for this were 4,000 RPM forward to 4,000 RPM reverse in approximately 2 to 4 seconds, depending on how big of a chuck you have mounted. So essentially, I just went through and replaced every wire one by one. There was a broken wire leading to the transformer back here. There's a little, it's probably hidden, but it's behind the field tube. The transformer back there is essentially triggering the two thyrotrons. And so one of the wires going to it was broken. One was completely detached, and the other one was broken inside the insulation so that it would intermittently make contact. The wire that I thought might be a concern, there was a lug under here that was tightened down onto another wire. That was not an issue. It didn't penetrate through the insulation. So this was pretty straightforward, essentially just 2 broken wires. But all the wiring was replaced and labeled, and I might do a better job of routing once I've ran the lathe for a while and determined that it's going to be stable for a foreseeable amount of time. And then I might do the nice neat wire tie where they had it wrapped and tucked a little bit better than I have it now. But I have it in primary bunches, the one's going over here, the one's going over there, the one's going to the back. I got a little bit of wrap on that just to keep them together. And so the only remaining things to do are there's a terminal back here, and this wire, all these wires right here either go through some conduit in here, or they go to the terminal strip that's on the side over here. And I just want to kind of make sure nothing's going to rub through. And not that this is going to be open or closed very often, but I just want to make sure all the wires are kind of tied back and tucked and routed properly. I also have to route the blower wiring. So normally this will be completely closed in operation. And there are some calibration potentiometers inside of here, and I've gone through that. So one will set your max speed, and the other will set your load compensation. So if you're taking a heavy cut, it needs to be able to sense that there's an extra load to increase the pulse width that the thyrotrons are allowed to pass through, which gives you more power so that you maintain a constant speed. So it's just an analog feedback circuit that handles all that. Simple and elegant, but very confusing to try to figure out what's going wrong. Alright, so in here, the only problem I found was this ring terminal was broken on the original wire. That's the armature. It's A2 going to the anti-plugging relay, and so this is what you can have it at 4,000 RPM forward and then flip it to reverse, and the machine will break the motor, and then once it gets below a set RPM determined by the settings on this little tension adjuster here, it will allow the reverse contactor to engage to go into reverse. So basically it keeps you from engaging reverse while the spindle is moving forward. So I believe that was the only major issue in here. There was a few terminals that were loose. there was a little bit of, not corrosion, but arc damage. This right here is what essentially, when you if you want to slow down quickly, it's called a quick slowdown. But the change in armature current causes a field to develop here, which engages this, and this will causes the armature leads to the motor to get bridged, where the EMF is slows down the motor quickly. Dynamic braking. It's basically just like in your hybrid car, although that's regenerative braking, but it's a type of dynamic braking, so that you're using the electric motor's field as an internal brake, so a non-physical brake. And I still haven't put all the covers back on. And so, like I said, a lot of this is just getting it all running, having a shakedown, making sure everything's going to be alright, and then I'll button it up. Alright, so coming up we got 3 clips to take a look at. A couple of them are shot with my old cell phone, and the video quality is not that great on it. But it's just essentially some close-ups of the tube section while I'm operating the lathe and some problems I encountered. I'll give a little more detailed intro to each clip separately, just to kind of let you know what's going on at that time, and we'll just take a look at that now. Alright, so in this first clip, we're going to see what happens when you get the grid transformer out of phase with the anode transformer. So this right here controls the C16Js, and you got your primary side, secondary side, center tap. So these are 180 out of phase. This is similar to the anode transformer, except the anode transformer is huge. And so if these primaries are out of phase with the anode transformer's primaries, that means the secondaries are also out of phase. So it tries to trigger the C16Js at the wrong time, and you kind of get some crazy results. And the reason why I pulled this one out of the machine is because I couldn't really identify. I tried Googling that part number at the time, and I never could find out what this actually was. I set this one up on a little test jig, and I was having some asymmetry between the 2 taps on the secondary here, so I just went ahead and replaced it. And so I just ordered a stand-core generic replacement that fits the specs that were originally called for in the design. So anyway, we'll take a look at this clip. Second video is going to be of this guy right here. He gets a little trigger happy once he gets warmed up, and so when this thing starts firing by itself with no trigger signal on the grid circuit, then it prevents the other tube from firing. My guess is that it changes the entire biasing system, since it's firing at such a negative voltage on the grid. Then the grid voltage never gets raised enough to fire the second tube. So whichever side this one was in, the problem followed this tube. This one would continually stay on after turning off turning the spindle speed down to 0. And so what happened is I looked into an eBay ad showing EL16Hs, and so I could not find a data sheet on these anywhere, so I emailed Richardson Electronics, and they were nice enough to send me one. And the only difference between the C16Js and the C16Hs are the maximum voltage. So right now in the lathe I have an original Raytheon part beside one of these Electrons company C16Hs. Alright. So that's pretty slow, 50 RPM, 200, it's got a little bit of a load, not And then it starts doing this. That's all the way down. And it's getting faster. So spindle off. Same thing in reverse. $1,000, $1,250, $1,500, $2,000, $2,500, $3,000. $4,000. Dynamic brake worked. And that's all the way down, and we got 200 RPMs. Red button. So the third video shows the lathe working, everything's doing its thing, both tubes are staying lit, forward, reverse, got all my speed range. The problem with this is all the vibrations and weird kind of noises you hear. I mentioned in the video, but going back and looking at it, it's actually kind of worse than what I mentioned in the video. So here we are, got the power on, it's warming up. It's got a 1-minute timer for the heater for the tubes, for the big tubes, maybe the small tube too. I know the large ones, the C16Js, have a 1-minute warm up. And so that little bit of a buzzing sound was the timer closing the circuit. So now I can control on, which will turn on the center tube, give power to the field. The field has to stay on at all times. If it's ever under power and loses the field, you have a runaway situation with the motor. And so that's one of the safety features. There's also a field loss relay, so if the field ever loses power, it shuts down the machine. So anyway, I'm going to go turn it on real quick. So that's the field. I got a little bit of transformer hum. I've gotten back there and poked around. There's not a whole lot of loose stuff back there. Could be the fact that I have it on a wooden pallet. It's resonating a little bit. So anyway, make sure I got everything. Turn my speed down. So we're going to engage the spindle. So that's the contactor there. And I'm going to turn the speed up. So that's turning pretty slow. Maybe 100 RPMs. I'm not running in back gear or anything. So we'll get up to, it's about 600. So it's running pretty well. Sounds good, nice and smooth. Just a lot of transformer hum. It's not pulling any excessive current. It's just got a fair amount of noise. I mean, the motor hums and the transformer hums, but I mean it's getting a dirty DC. I mean, it's essentially a DC pulse, 120 hertz. So I'll get the spindle going, and I'll turn it down to something reasonable for me to grab hold of it. So here we are at about 100 RPMs. So I'm going to try to hold it still. So you can see it increases the overlap between the trigger signal and the anode voltage is 2 AC waves. And so the more overlap, the more area under the curve or the sine wave gets to the motor. So that's essentially how it functions.
So everything seems to be working. I'll load the spindle one more time. So I got forward and reverse. If I go too fast, there's something, it sounds like a coupling, something clangs in the drive system, and to me it sounds like something thin and light. So if it were a regular motor, I would say it was a loose fan on the shaft, but for this one I haven't had this one apart to look and see. As long as you're going a fairly smooth change in velocity, you're okay. But if you try to do something abrupt, if you have the spindle speed set really high and you go from off to on, and you'll get a clang. So I'll have to figure out what that is, but I don't think it's anything horrible. Alright, that pretty much wraps it up for this edition. I think the next thing I'll show overall is just a little quick cleaning video, and then we'll get back to investigating noises, getting the blower installed, and all that good stuff. See you next time.